So our next speaker is Olgica Milenkovic. Yeah. Going to talk about clustering in genomic data. Excuse me? Hello? What? I love genomics? Excuse me? We're going to get going? Hello?
Hello.
All right, after this wonderful panel. So our next speaker is Olgica Milenkovic, talking about clustering in genomic data.
Okay, I think we all needed a little break here, so computational problems with the clicker, but I'm really glad to be here today, and I would like to thank the organizers for inviting me. And I'm really glad that I'm talking a little bit later in the day, because a lot of the topics that I will mention in my discussion today are closely related to issues that were brought up by previous speakers. So today I will talk about an algorithm a type of algorithms that everyone who ever worked in bioinformatics must have encountered at some point of time. There's absolutely no one in the audience who never worked with clustering. So let's assume that you all cluster data left and right. And today my talk is going to be on a new type of or form of clustering, higher order clustering. And I want to show you that the machine learning community has been going back to its roots in terms of some basic algorithms like clustering algorithms and trying to reinvent itself. And the main part of my talk will be to discuss what machine learning researchers have been obsessing with in the area of clustering, and in particular something called higher order clustering. So you heard in Trey's talk and other talks that it is very important to look at higher order structures. So if you have graphs, for example, you're so accustomed to looking at links or pairs of vertices or edges, while we all know that everything in networks is organized based on higher order structures, such as subgraphs or network motifs. And in order to get, for example, hierarchical network structures, you would also have to look at these higher order structures. And this is what I'm going to talk about, higher order clustering and some constrained versions of it. So just to recap what I started talking about, you know that clustering is an integral part of many multi-omics data processing pipelines. And I leave it to your imagination to think of one application or one bio problem where you use clustering. And if you ever worked in clustering, the first thing you would do is to check out what kind of algorithms are out there that you could use to solve your problem. And whatever you learn first is probably k-means or km. Then if you're a little bit more elaborate in your research, you may have run into the topic of spectral graph clustering or spectral methods for clustering. Much less likely, but still pretty useful, if you were searching the theoretical computer science literature, you may have seen something called correlation clustering, and I mentioned it briefly this morning because some of the speakers were really looking at something that looks like correlation clustering. And more recently, people have been obsessing with a fuzzy form of clustering that comes from this notion of non-negative matrix factorization, and in particular in the context of single-cell RNA data analysis. And what happens usually is that you know of all these algorithms, you Google, and you find some of these methods that seem to be good, work well for certain types of problems. And what you usually do, and there is no offense meant, is you use these algorithms off the shelf, and you believe that these algorithms are all well understood because they have been around in the community for a long time. So just in case that these algorithms are not well understood and that you may not have seen them before, I'll briefly review 4 of these algorithms that I mentioned, and then I tell you a bit about the directions that the community is taking in this context. So everyone, as I mentioned, knows k-means clustering. The basics is that you're given a set of points, a distance function or similarity function between the points, and then you find your major goal is to try to find the centroids of k clusters where you assume that k is usually a number given beforehand. You have some Gini kind of knowledge about the number of clusters, and you're really optimizing this potential function that tells you minimize the sum of all the shortest distances of points to the cluster centers. And it's an algorithm that we know is hard to ensure that it works properly. It's a computationally hard algorithm as well, and it usually is operated by running an iterative procedure where you randomly choose cluster centers You randomly choose cluster centers. Then you divide the points based on the distance to the cluster centers. You recompute the centroids, and then you iterate. And more recently, or not so recently actually, at least 15 years ago, people started looking at different initializations rather than random centroid initializations. And this algorithm k-means ++ is one of the most popular initialization methods for k-means clustering, where you basically try to choose the initial centroids not in terms of uniform at random sampling, but you try to sample points sequentially and make sure that when you sample a point, you sample something that's sufficiently far from it, thereby hopefully reaching all the clusters that are in the set of points. So other than that, another class of algorithms that you may have used before is graph clustering. And in a graph clustering setup, you can do a lot of different things. The idea is that you're given a graph where you have edges, which are endowed with some weights, and then you're given a clustering objective function. And that objective function usually depends on the topology of the graph and the weights of the edges. And the objective is to optimize some function that depends on the topology and the weights. And then you can add constraints such as how many clusters you want. Do you want the clusters to be balanced or not? Do the clusters have to have some overlap? And so, for example, this would be a case of graph partitioning with a roughly uniform size of clusters. This would be an overlapping graph partitioning problem. So a lot of these have been around for a long time. So the idea how graph partitioning is done is usually in terms of this notion of a cut, and I will just explain to you in a second what it really means. If you want to partition a graph into two parts, and you find basically two communities or two clusters, usually the goal is to minimize the total density of the edges or the weights of the edges that cross between the two clusters. So you usually define what is called the boundary of a set. If this is a set, this is another set. This is how you want to partition your vertices in a graph. The boundary would constitute the edges that cross the line between the two clusters. And then you define nothing more than something called a cut function. And using the cut function, you come up with an objective, which is the normalized cut, and optimize it using spectral methods. And I won't go over it. Very simple methods that involve computing a scaled version of an adjacency matrix, which we call a Laplacian, and then computing the eigenvectors of the Laplacian, and running k-means on the eigenvectors to obtain the clusters. And the third method is an agnostic clustering method. And it's a very interesting method which came about actually from people here at CMU in the computer science department. The goal is to learn the number of clusters along with the solution for the clustering. So it's agnostic because you don't need to know the number of clusters beforehand. And it's called correlation clustering. And it has been investigated in many, many different settings and forms, some of which also involve motif structure or higher order structures. But I'll comment on that a little bit later. And finally, the fourth major category of clustering algorithms that has been heavily used recently is this form of so-called non-negative matrix factorization. And the gist of the approach is basically to deal with the matrix in terms of a representation that involves a product of two non-negative matrices. And you can think of one of the matrices, W, in this product representing the centroids of the clusters, while the other matrix tells you a weight of the jth unit in terms of its propensity to belong to the ith cluster. So the matrices encode information about the cluster structure and the probabilities of the points lying in these clusters, and hence this is something like an overlapping clustering or fuzzy clustering framework. What is really interesting is that recently, most recently in 2013, people have looked at multi-view clustering approaches, which are very favorable for clustering of multiple data sets that share some ground truth. And in this context, you really are trying to optimize a function that involves multiple factorizations of a matrix or multiple clusterings and merge them into one. And I won't go into details. If anyone is interested in it, I can take it offline. So these are the basic 4 algorithms everyone has seen, most likely in some shape and form. And you would have think that these algorithms have been out there forever and that nothing more is happening in the field. But very recently, conferences such as ICML and NIPS have been starting to look at completely new clustering paradigm. So one of these issues, or one of these types of clustering, is this clustering with pairwise queries. So this is a paradigm which is very exciting because it shows that if you have a set of seeds for your clustering problem, then some problems like the k-means problem, which is NP hard, become actually computationally tractable. And this line of work on clustering with pairwise queries only came about in 2016. And it asked the question, if you do k-means clustering, how many points do you have to have roughly distributed within the clusters used as seed points in order to be able to compute the centroids with 1 plus epsilon accuracy? And the answer is actually pretty surprising. You only need of the order of k cubed, if k is the number of clusters, points used as seedlings for you to compute the centroids of all the clusters accurately under certain mild conditions, and then just do assignments of points to cluster by simple pairwise comparisons to the centroids. And this is a line of work that we are computed or came up with a bunch of algorithmic solutions that also involve outliers, a really big problem in genomic data analysis, missing data, and if you're interested, there will be a paper on this topic in machine learning in the NIPS, at the NIPS conference this December. So the next topic is spectral clustering with constraints. So that is another area that has gained a lot of prominence only in the last few years. And it says that very often you have side information. If you're a biologist, you know that you would like to get your hands on some kind of side information or prior information that can go into the problem, make it computationally easier to solve, or produce more meaningful solutions. And in spectral clustering, in the last few years, there has been a lot of interest on these so-called must-link and cannot-link constraints. So let's assume you want to get a clustering, but you want to ensure that the clustering you obtain must have 2 points in the same cluster, or a bunch of points in the same cluster, and some other points are not allowed to lie in the same cluster. So if you have this kind of side information, then you can hardwire it into some of the procedures, and it's actually pretty interesting and not so straightforward to do it with spectral clustering. So people have been looking into this issue quite a lot in the last few years. So the other directions that the machine learning community is taking into account is extending, for example, this notion of non-negative matrix factorization into the domain of convex non-negative matrix factorization and non-negative tensor factorization. And there were a lot of questions earlier in the morning in the from the audience, what if you have dynamically changing networks? So whenever you have some kind of dynamical evolution of communities or networks, you would like to work with tensors, and this problem has been only brought to the machine learning community's attention in the context of non-negative tensor factorization just a few years back. And the applications are many. I would like to just point out that my group is working on single-cell RNA-seq data analysis with non-negative tensor factorization and some new methods. So other methods also include local clustering. So if you have a really limited computational budget, you only need to, and you're only interested in one type of cluster or just several clusters in your set, in your data set, then you can try to do the clustering locally and basically ensure some form of scalability. And again, despite the fact that the first line of these kind of works, even for correlation clustering and other types of clustering methods, has been reported about 10 years ago, it's only now that people are really looking at local clustering with great interest, because it's also something that Google and Facebook is quite interested in. And finally, hypergraph clustering. And this is what I'm going to focus my attention on for the next 10 or 15 minutes. And this is a completely new paradigm that started taking off in, in 2016, 17, and 18. And it refers to the fact that sometimes looking at pairwise similarities of objects or points in a data set is not the best thing to do, that you can exploit higher order structural similarities, small subgraph or motifs, in order to get much more relevant and important, relevant and meaningful cluster structures. So what is hypergraph clustering or higher order clustering? So think of a problem where you want to do community detection in biological networks. And Trey mentioned this. Community detection really is an area in information theory more than physics, and information theorists have been working on this problem for the last 4 or 5 years under the assumption that you have some model. And the models for the graphs that they used are so-called stochastic block models or extensions thereof. But one thing that the information theory community has largely ignored is the fact that in graphs, biological networks in particular, you're most often interested in some structures that involve more than 2 vertices. So these are what we call higher order network motifs or subgraphs that are of great importance. And in 2016, Benson and his advisor, Yura Leskovec from Stanford, published a paper in Science which says, okay, we can use clustering that involves triangles and come up with a network structure that explains how a food web or a food network in the Florida Bay area looks like. And the result was pretty exciting because it seemed like this was the first time anybody used motif clustering. But if you start looking into the literature, there was basically some hint of these results and this kind of work in the machine learning community at least 10 years ago. And here's how the formal definition of this problem works. You have a hypergraph, not a graph, but a hypergraph, which means you're given a set of vertices, but rather than given edges along with the vertices, you're given hyperedges, which is nothing more than subsets of vertices. These are your subgraphs or higher order structure that everyone is alluding. And so, for example, if I want to cluster, I can cluster, and you remember I mentioned the spectral clustering method, where I want to create a split in the set of vertices such that the smallest number of edges crosses the split or the cut. In this case, you may ask a similar question, but say that as few of the relevant hyperedges are cut. And so, for example, the hyperedges may be triangles, and here is one cut that cuts 2 triangles, but at the same time it cuts 5, 6 edges, but that's not relevant. You really only count how many triangles the cut splits. So this is what we call a cut in a hyperedge. And the question is, how do you do clustering with for hypergraphs using these kind of cuts or these kind of definitions of cuts? And the first and basic type of algorithm that people have looked at are spectral algorithms for hypergraphs. And these algorithms all rely on a very simple trick. They came about in 2008 or so, and they say, you know, we really don't know how to deal with higher order structures, with hypergraphs, so what we're going to do is we are going to project each hyperedge into a subgraph. So it's actually going the opposite way of what you think it would do. And that means if I have a hyperedge with 10 vertices, I would represent it as a clique in the original graph. And then I would merge the projected subgraphs into one graph and then run any of my favorite clustering methods, such as spectral clustering. So here is how these algorithms would work if you have motifs or hyperedges that involve triangles. This would be a graph that has one hyperedge here, one hyperedge here, another hyperedge here. So each of these hyperedges you would split into a clique. And in this case, since it's a triangle, the hyperedge and the projected clique look exactly the same, but the weights are split among the edges. If you had E edges, you will split the weight of one of the hyperedges into, this case, 3 parts, and then you would just sum up the weights on all the edges that you created and then run a spectral graph partitioning or clustering algorithm on the projected graph. So one interesting thing is, and this may be really relevant for people that deal with meaningful subgraphs or motifs in networks, is while you have graph cuts and partitions that involve edges, doing everything symmetrically That's not the case when you're dealing with hyperedges, because if I have, for example, a 3 hyperedge, then it may matter if one of the hyperedges, 1 ended up in one cluster and 2 ended up in another cluster, 2 and 3. 1 and 2 ended in one cluster, 3 ended up in another cluster. So the identity of the vertices and the way you split the edges or the subnetworks is really relevant. And this brings you to the notion of a completely new clustering paradigm, which is called inhomogeneous hypergraph partitioning. And here you're assuming that not all partitions of an hyperedge are equally awarded or penalized. And you can think of an example where you have a metabolic network and 2 of the entities in a motif are metabolites, another is for example, a control element or a transfer molecule or substrate. So if you cut the hyperedge, this triangle, by putting A in one cluster and B and C in another cluster, you should get a different penalty for the clustering algorithm as opposed to when you put B and A in one cluster and leave C in another cluster. So this notion basically can be shown to give very interesting results, because you can run it on some very straightforward examples like this graph and see that inhomogeneous partitioning, homogeneous partitioning of hyperedges, and just plain vanilla graph partitioning give you very different results. And this is just an example that illustrates how you can get the community structure or the clusters that you're after to really change their shape and structure based on how do you decide to penalize which higher order structure is split in which way. So how much time? Oh, 5 minutes, okay. So one thing that I want to mention before I do an example, I didn't realize I already spoke for this long, is that this is a very difficult problem, because our understanding about homogeneous partitioning is just to try to project the problem into a graph structure, while this problem of inhomogeneous partitioning asks us to basically look at different costs of partitioning elements in a network motif or in a higher order structure. So one theoretical result that was very hard to prove, but we managed to do so, is to show that when you do projections on higher order structures and then you do classical clustering on the graph, that in some cases you can have a constant approximation of the cut costs in the hypergraph with respect to the cut costs in the ordinary graph. And this is true only if the weights have a very important property, which is submodularity, and it works as long as your motifs or your subnetworks are not larger than size 7. So if you have subgraphs that are of size less than or equal to 7, all these projection methods will work, are guaranteed to work, and not give you approximations that are worse than twofold compared to the original hypergraph clustering problem. So I'll skip some of these things and I'll show you how these hypergraph clustering methods can actually give you hierarchical networks that you expect to see, where you use meaningful subgraph structure to infer how a system of interacting entities behaves. In this case, the well-known example of this Florida Bay food web. So if you plot the Florida Bay food web, you will just see a mingled collection of vertices where you really don't understand or know what are really the cluster structures that you're after. But one thing that you're really interested in and you're aware of is that most biological networks, as Trey mentioned in the morning, are hierarchical structures. And in this case, it's pretty obvious because you have producers, primary consumers, and a bunch of other entities that are all feeding off of each other in the food network. So we would like to get a hierarchical clustering structure for this network, and we want to use the fact that we are doing higher order clustering that involves subnetworks. So if you look at the way to do it, it's actually pretty straightforward. So I have a graph like this. So I'm going to do the following. I'm going to convert the graph into a graph on which I observe higher order structures of this form here. Higher order structures that involve 4 vertices, 2 vertices lying in one layer or in one level of the hierarchical clustering, and 2 vertices that lie in another level. And I'm going to only allow connections between vertices in one layer to the other layer, but not connections between elements in the layers themselves. So For these structures, I will impose some weights on how do I split the structures that are present of this form in the network. So for example, isolating a vertex may cost 1. Isolating V1 and V3 from V2 and V4, which is not a good idea because it's going to ruin the hierarchical structure, will be penalized with cost 2. And V1 placed in the same cluster with V2 versus V3 placed in the same cluster, and V3 placed in the same cluster with V4 will incur no penalty at all. So what is really happening is that we are forcing pairs of vertices to lie in one level of the hierarchy as long as there are no edges between them, and allowing these vertices to only connect to vertices in another hierarchy, in another level of the hierarchy where there are no edges between them. And what we get is an amazingly beautiful and simple hierarchical network structure. Because if you see this, you exactly see the producers, invertebrate, forage fishes, predatory fishes, and top-level predators popping out in the hierarchical structure, and only 6 links appeared in this network in a reversed order. So while we were hoping to see this link here go in the direction indicated by this directed network structure, it would go the opposite way. Basically, this predatory fish would feed on this forage fish rather than the other way around. So this comes about by using only specific network substructures and clustering that involves only these substructures, and you get beautiful hierarchical networks with a lot of correctly quantified links and vertices. So this is the result you would get if you used, for example, classical clustering method. You would get a bunch of clusters that don't seem to have any structure in them, and you would get tons of vertices that are not classified at all. And this is a result that appeared in Science in 2016, and it's a good idea, but it didn't go the right way because the motif was chosen to be a triangle, which doesn't impose a hierarchical structure. And there were no different costs for penalizing how you split the triangle, so it created a mess of multiple networks being connected to each other through a group of unconnected networks. So I'll conclude by saying all these graph or hypergraph clustering methods have found so many applications, and if you haven't seen them before, I really strongly urge you to look at whatever is out there in the hypergraph clustering community, because it can be used to learn categories in ranking models. If you work with gene prioritization and other problems, you will run into a lot of questions related to hypergraph clustering. If you do subspace segmentation in imaging, or if you work in many problems from computer vision, you will see hypergraph clustering problems. If you're trying to use mutual information as a measure of strength or quality of some links in biological networks, you will end up most often using hypergraph clustering methods to estimate mutual information. And one thing that I would really like to hear more about from the audience is what other applications of motif clustering one could think of in diverse biological networks. Clearly, you can use it in gene regulatory networks, protein-protein interaction networks, food networks, but any other examples would be very welcome. So thank you for your time.
So, thank you for an amazing talk.
I'm so glad to hear you didn't think I lost the audience.
So this may be a naive question, but how sensitive is this particular model to batch effects, other types of noise, and incomplete information?
Yeah, that's a great question. So all of these clustering methods, the machine learning community, and my group in particular, is coming up with outlier identification and isolation methods. Basically, you can take outliers out, you're sacrificing clearly on the precision, but it's under the assumption that outliers are points that are far away. If you do, for example, k-means clustering, far away from any normal cluster. So you have to use something like a gamma margin assumption for outliers. Missing data and erroneous data, all of it you can handle by just rerunning things. Depends clearly on how much. If everything is wrong, you can characterize analytically how many errors can you tolerate for each of the given algorithms. And all these directions, I think, I forgot the name of the person that visited Urbana recently and gave a talk on it. It's one of the biggest interests in Google and Facebook and Microsoft research these days to really find what outliers are in networks. And that is a problem that the machine learning community is really hyped up with. So outliers in particular, I think we now have a pretty good understanding of how to deal with them in clustering under certain conditions, basically that the outliers are sufficiently far from all the cluster structures and that there are not too many outliers. Yeah.
Another question over there?
So when you set the penalties for the connections that you don't want to see the clusters, how do you choose the numbers?
Oh, so I mentioned we want to have things that have theoretical guarantees. So we work in an area where if you don't have theoretical guarantees, you're going to be shut down immediately. So I mentioned that if the weights are chosen to be submodular functions, then we have guarantees that whatever we get with this method will not distort the cost of the original hypergraph clustering by more than a constant factor. Depends on the size of the hyperedge, as long as the hyperedges are not too large. We have a follow-up work at ICML this year where we showed that you don't need to do projections. You can work with a new notion of Laplacian for hypergraphs, and then you can technically have no distortion. The problem is that you have to pay a computational cost. The algorithms are more complicated.
All right, thank you. Let's thank our speaker again.